Hello friends, welcome to MES e-learning channel. So today in this particular video we are going to study the use of a spiral binding spring to study buoyancy and to determine the density of air. So two things we are going to do. First of all, we are going to use very simple material, as simple material as this spiral binding spring which you normally see in any book binding. So I simply remove that. We are using this and nothing else, and weights which are as simple as this one. So we have 4 weights out over here. This is the 20 grams, this is 50, 50, 50. So totally this makes about 170 grams this way. So let's proceed with this one. So here is, first of all, let us understand what do you mean by the buoyancy. So buoyancy is nothing but the upward force that is exerted on a body by the fluid in which it is submerged, and this is called as the upthrust or the buoyant force. So as you see over here that the weights are actually dipped. You can see that the weights are actually dipped in this, the water over there, and because of this there is an upward thrust that is actually been built up. So I am using this particular spring. So whenever it is in air, right, it will have some extension, and whenever it is in water, since because of the upthrust it is going to go low. So I am going to measure this upthrust with the help of this marker, which normally is on a scale which I am unable to show it over here. But this particular the scale is of course shown in the screenshots. So let us go to the very first step, and the first thing which you are going to do is calibrate this particular spring, that for a particular extension what does the weight correspond to, or going the other way, for every weight what is the extension that I am measuring. So first what we see we study a little bit regarding the setup. So here is shot of the setup. So first this is the scale, the meter scale that we are using over here, right? And this is the extension, the weight actually which is being suspended over here, and then we measure the extension of this particular weight on the scale. So this is how we measure the extension in air of any particular weight. Next, what we are going to do is we are going to find out first of all what are the different kind of extensions which are there in air, and later on we are going to find out what are the extensions which are there in water. So the list which you are actually seeing is there is a zoom up of the springs, the values of the springs which are there for the different weights. So the different weights that you are actually having is, the first weight will be is corresponding to 70 gram, followed by the second one which is actually corresponding to 120 grams, and addition 50 to that, that is 170 gram. So we have suspended the weights using the spiral bending spring in air, and the values of the extension are 27.5. This is for the 70 gram weight, followed by 24.7. This is for the 120 gram weight, and 21.8. This is for the this is the extension, that is 21.8 extension that is showing on the scale for the 170 gram weight. And similarly for the same weights, that is 70, 120 and 170, we are having the corresponding extensions when these weights are dipped in water are, this is 27.7, 25.1 and 22.9. So immediately you will see that these extensions are less, the extensions that you are actually seeing on the scale are less for the same weights when they are immersed in water. So we actually are, in a way, we are confirming the buoyant effect of that is exerted by the upthrust rather, that is exerted by the liquid, in our case that is nothing but water. A graph is the best possible way in order to see this particular data in a very pictorial way, in order to see the variation which is there. So let us now plot a graph of these particular values, and this is the graph. Now immediately you will see that on the y-axis what you are plotting is nothing but the extension that we are seeing on the scale, and on the x-axis we are actually plotting we are taking the weights with which the spring was actually suspended. And you will see that we are getting a little bit absurd relationship wherein as the weight increases, right, right, the extension is actually decreasing. And the reason is this: I did not minus each of these extensions from the reference value. This means the reference value for one particular weight which is there, and we took this reference value for the 20 gram weight. So let us see what happens then. So this is the reference value, and the reference value, suppose we are taking it, is actually 30.3, and this particular reference value which you are taking, and this now we are now subtracting each of the extensions that we are obtained before from this value, that is 30.3, and therefore we are getting the new values. So for 70 grams the extension that we find is 2.8 centimeter. For 120 grams the extension that we find is 5.6 centimeter, and for 170 grams the extension that we find is 8.5 centimeter. Similarly, now let us also do the same kind of corrections for the readings that we are obtained when the weights were suspended in water. And the corrected readings now, that is actually giving you the correct extensions in centimeters, are 2.6, 5.2 and 7.4 for the respective weights. And immediately you will see that there is a difference between the two. And whenever the extension is always less for the same weight, right, for the same weight in air, when I'm suspending the same in water, the extension is less. And this of course proves the upthrust which is there, and this is of course happening because of the upthrust or the buoyant force that is exerted by the liquid. Now we make a plot of this one, and when we make a plot of this, now we find that the red line of course are the values, which is the values for the extension versus the weight, right, and for whenever it is in water, and the black line, the black trend line, is for the values in fact which are taken in air. And you will see that these values that are represented by the red line are always less than what are actually represented by the black line, which is for the air. And once again you see a very a prominent proof, that the graph gives you proof that indeed this is correct, that the extensions are indeed less whenever the same weights are actually suspended in water, and that is because of the buoyant force or the upthrust that is exerted by a liquid. So here we have taken water, you can always try it for any other liquid also. Now, so we are confident about this, that our system is now working. So why not apply it to find out, let us say, the next important concept is to find prove, let us say, the Archimedes principle, right? And after that we will try to do one more application, and there is nothing but to find out the density of an unknown solid. So let us go ahead with that. Okay. So these are the readings which you are actually seeing are nothing but the extensions of unknown weight, and even the density and even the material. Of course we knew that it was actually soft iron, but this is an unknown shape which is there, and the weight was also not known to us. But now we have calibrated our system, and wherein we know that for every 10 grams of extension, for every 10 grams, whenever it is suspended with 10 grams, this spring is going to get extended by an amount of 0.45 centimeters. So these are the values which we have actually obtained from. So let me go back for a minute. So these are the values that we are actually obtained from here. So we have taken averaged it out, and then we found out in fact that what does every 10 gram of extension corresponds to, and the 10 grams of extension indeed we have reported there is actually corresponding to around 0.45 centimeter. So that's the way we actually calibrated our system now. So using that, now we are coming to this to this case of the unknown shapes solid which was there, unknown weight solid which was there, and that was actually suspended in the same experiment we did. First of all, we suspended that in air, and we found out the suspension of that. We found out the extension, because of this suspension, and the same solid once again we put it in water, and then we found out what is the difference in the extension, right. But prior to that, before going ahead with the details of this particular slide, I will request you to please watch this particular video that gives a, that will give you a feel what of the way in which we carried this out in the laboratory, and then we will return to this particular slide. Okay, so having watched this particular video, now we go to the details of this particular slide. So the first thing that we are looking out is the extension that occurs of the spring because of this unknown weight, and this extension we find it to be 28.2 centimeters. Now this extension, as you know, is not the correct extension. We will have to subtract it from the reference value, which is 30.3, and therefore the correct extension is coming out to be 2.1 centimeter. Using our basis, that is for every 10 grams, this will correspond to an extension of 0.45 centimeters. We are taking a direct proportion, and therefore the unknown weight in air is found out to be 47 grams. Similarly, now we dip the same weight, as you must have seen in the video. We dip the same weight in water, and now we measure the extension. And this particular extension is turning out to be 30.3, actually it is turning out to be 28.5, but when we subtract it from 30.3, it turns out to 1.8 centimeter, of course less than the one which we obtained in air. And therefore, the weight as we are measuring in water is turning out to be 40 grams, okay, using the method of direct proportion. So now we go to the next one, and hence the thrust that we are actually measuring will be the difference in the weight in air, and the difference between the weight in air and in water, that is turning out to be 7 gram force. So the volume that we actually measured was, the volume fell down to 30 cc, and that minus the upper level, so that comes out to around 7 cc or so, or a little bit more than that. But as you must have noticed that when we actually took out that object from water, some of the water was also, in fact, it actually smeared with the object itself. It got away with the object itself. So making some room for that particular correction, we took out that the volume of this particular solid must be around 7 cc. And of course, the weight of this volume of water is will be around 7 grams, because taking into consideration the density of water, that is 1 gram per cc approximately, and this of course will equal around 0.007 kilogram force. Now, while the upthrust which you already measured before, that was nothing but the upthrust was nothing but the difference in the weight of this particular solid, that came out to be around 7 grams, and that is nothing but 0.007 kilogram force. You see that both the values are actually matching. And what does this prove? This proves that we have indeed verified Archimedes' principle, which states that the upward buoyant force that is exerted on a body immersed in a fluid, whether fully or partially submerged, is equal to the weight of the fluid that the body displaces. So this was one application. Now let us go to the next application. And the next application is of course finding out the density of this unknown solid. We knew that this particular solid is actually made up of cast iron, and we use this particular formula, that density of the solid, that is cast iron, is nothing but weight of the solid in air divided by the loss of the weight in the liquid, that is, or the fluid, which in our case is nothing but water, multiplied by the relative density of water, which is of course 1 gram per cc. And doing and putting in the respective values at the weight of the solid in air, which turned out to be 47 grams, and the loss of weight in the liquid, which is equal to 7 grams, that is 47 minus of 40 grams, which is 7 grams. This works out to be 6.71 grams per cc. And the reported value of the cast iron density is actually 7.13 grams per cc. So it is well falling within the range of the reported value. So once again, using a very simple experiment, using simply spiral bending spring that is there, a plastic spring which is there, we could actually prove two things, that is the Archimedes principle, and of course we also obtained the density of this of the unknown solid which is there, and that is cast iron, and this turns out to be 6.71 grams per cc. So the point which you are trying to make out over here is we can try out such simple experiments in the lab, okay, and we can in fact come out with more amazing results than even what I have got in this particular video. Okay. So thank you very much students for listening to this particular video. Thank you very much.